Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's our pleasure today to have Mario Marchand from Université Laval in Quebec City. And he's come here to talk to us about PAC-Bayesian machine learning, which is learning by optimizing a performance guarantee. So, Mario.
Thank you. Thank you very much. I would like to thank Offer Dickel and Microsoft Research for this kind invitation. I'm having a terrific time here. I think that the people here are very interesting, very kind. So it is a terrific place to be, and I'm just very happy and very honored to be here. So this is perhaps the title resume most of our research that we're currently doing at Laval University in the group machine learning group, which in French is the group of apprentissage automatique de Laval, which happens to be the same name of the Holy Grail, which is a nice coincidence. So this is our group, and basically we're two faculty members, me and François Laviolette, who is also another professor, and these are the grad students, some of the grad students that actually participated in the result that I will show you today, but we have also other graduate students. And basically the title resumes a bit our main line of research, that is whenever we try to design a learning algorithm, we first try to find a good performance guarantee and then propose the learning algorithm that will optimize the performance guarantee. So before outlining the talk, basically I will just present a few slides to introduce the notation and the basic supervised learning setting. So in the supervised learning setting, we have a training set of M examples. So each example is just an input-output pair. So this is the input and the output associated to input X. So the input space is usually arbitrary, and the output space will basically define the kind of supervised learning problem that we have. So this is, if the output space is -1 or +1, this is just binary classification, the real set for regression or a real interval for regression, and an arbitrary structured set for structured output prediction. So all the theoretical, well, basically the only assumption behind the theoretical results is this assumption here, that each example is drawn independently according to the same distribution on the input and output space. So that's what we assume, that the training sample, each element of the training sample was drawn according to this distribution. So the goal of the learner or the learning algorithm is to find a predictor having minimal risk. So this is the goal of learning. It's always that goal. So, and the risk of a predictor is basically defined as the expected loss, the expectation performed according to the real data generating distribution. And the loss here is expressed in terms of a loss function that measures the loss incurred on predicting h of x when the actual output is y. So, of course, the learner, so the problem is that the learner does not know the distribution D, because this is the objective of the learner, and it is defined with respect to D and not with respect to the training sample. So we don't know D, we have only access to a training sample drawn according to D, and so the central question in supervised learning is what should be optimized on the training sample to obtain the predictor with the possible minimal risk. So this is the main question in supervised learning. And the usual way to answer, well, we basically avoid this question most of the time. Basically, we'll say, well, we don't exactly know what should be optimized on the training data. So let us just try to guess what we should optimize, and we would basically just propose a regularized risk functional, so that would typically be like that. It's not always like that, but you always have an empirical risk of the predictor, which is just the empirical loss measured on the training set of example. And you have some complexity term, penalty term, which depends on some complexity measure of your predictor. And lambda is some positive real number which we don't know its value, so we normally choose it by cross-validation. So basically on the testing, cross-validation on our data. So perhaps we can do better because, well, this is the normal way of doing things. We propose that, we find that it works empirically, then there is theoretical person that's proposing some bounds and some justification why it's not a bad idea to do that. But can we do better than this? So if we cannot find the predictor with the best possible risk, so let us just try to find the predictor with the best risk guarantee, and a risk guarantee which can be computed on the training data. So let's try to do that instead. So the guarantees that we have are called risk bounds. So these are the theoretically accepted guarantees that we have. And it's called a risk bound. So a risk bound is just basically a function of the predictor, a training set, and some confidence parameter. Normally, it just weakly depends on the confidence parameter. And the property of the risk bound is that with high probability, with respect to random draws of the training set, it's basically simultaneously for all predictors, the risk is upper bounded by the bound. And the bound is really here the random variable, which depends on predictors and training sets. So basically, the optimization problem for supervised learning is then to find the predictor minimizing the bound. So this will be the predictor having the best guarantee, which can be computed on a training set. So this is basically our direction of research. So this makes sense, of course, if you have a good guarantee, a tight bound. If the bound is not tight, well, perhaps it won't give good result empirically. So we approach supervised learning problems basically by first trying to derive a risk bound for a particular learning setting, which can be computed for any pairs of predictor and training sample. And then once we have the bound, well, we design a learning algorithm for minimizing it, given a training set S. And so basically it will return the predictor with the best possible guarantee. So for step one, basically we use the PAC-Bayes theory. Why do we use PAC-Bayes theory, which was initiated quite recently by McAllister in one of the Cold Conference in 1999? So first, it can give very tight risk bound. It's not because you're doing PAC-Bayes theory that you're going to find tight risk bound, but you can really obtain tight risk bound if you're putting the effort. Also, it is about distribution. So basically, it's about distribution over class of predictors. So it gives guarantees to ensemble methods such as boosting, SVM, random forest, kernel methods, many state-of-the-art learning algorithms, basically. So it gives a guarantee to methods like that. And perhaps the most important point I have not written here, it's quite easy to master. PAC-Bayes theory is very simple. It's much simpler than a VC dimension and even Rademacher complexity. It's really something that a graduate student can understand fully. So this is certainly one important point. So this is the outline of my talk. So since it's easy to master, I think it's a good occasion to explain you the elements of PAC-Bayes theory. So you will leave the talk, I think, with the main ideas behind it. And if you work a bit more, you can just master the technique. And then we're going to apply that to some particular cases. So the first case is going to be on Gaussian distribution over a linear classifier. So this is a kind of posterior distribution over a very important class of predictors, linear classifiers. We're going to also to talk about PAC-Bayes sample compression. So this is recent work. We happen to present that at ICML 2011, so very recently. And so basically the idea here is basically we're going to use the PAC-Bayes approach, but on a set of classifiers which are described by the training data, by subset of the training data. And finally, perhaps I will just outline some work that we're currently doing right now. Okay, so elements of PAC-Bayes theory. So, okay, here we restrict ourselves to the simple classification case. So we consider the 0-1 loss, so the true risk of a predictor and its empirical estimator on a training set S are just defined respectively as, this is the indicator function, so it's 1 if the predicate is true and 0 otherwise. So it's 1 when you're making a mistake, and so this is just the probability of making a mistake when you draw an example from the data generating distribution, and this is just the frequency of error on your training set. So the learner's goal then will be, so the output of the learning algorithm will be to produce a posterior distribution Q that depends on the performance of individual or collective classifiers. So basically, we're going to produce a posterior distribution on the space of classifier such that the risk of the Q-weighted majority vote, that I call BQ because sometimes it's also called the Bayesian classifier, but here let's call it the majority vote or the Q-weighted majority vote. And we want to obtain a Q-weighted majority vote that has the smallest possible risk. That's our aim. Okay. So PAC-Bayes bound, in fact, produce bounds on the risk of the majority vote indirectly, because it bounds the risk of another classifier, which is a stochastic classifier. The majority vote is deterministic. On each example, it always output. If you present the same example twice, it will output the same prediction. But the Gibbs classifier is something different. It's stochastic. So to predict the label of an input example X, the Gibbs draws a classifier from H according to distribution Q, and then predicts the label of X according to H of X. And so if you present X twice, it might predict different labels because it's stochastic. The draws might be different. Then the risk and the training error of the Gibbs classifier are just given as follows. So it's just the expected risk, where the expectation is done with respect to the draws according to Q. So this is Gibbs risk, and this is Gibbs empirical risk, which is just the expectation of the empirical risk of the individual predictor. Okay, so what is the relation between Gibbs risk and the risk of the majority vote? Well, you can bound the risk of the majority vote by this equation. You can easily prove that the risk of the majority vote is at most twice the risk of the Gibbs classifier. So if we provide a risk bound for the risk of the Gibbs classifier, we will automatically have a risk bound for the Bayes classifier, but via this factor of 2 rule. So we might lose a bit here because of this factor of 2 rule. So the way to understand how come we have this relation is basically you consider an example. Consider a fixed example xy. And consider the two cases when the majority vote makes an error on this example and the case where it does not make an error. So suppose first that it makes an error on this example. So if it makes an error on this example, it means that half of the classifiers under measure Q will make an error on it. So half of the classifier will make an error of it. So this means that, so it could be 1/2 plus epsilon of the classifier that will make an error on it. So this means that twice as the error on that example of the Gibbs will be greater or equal than, because now the risk on that example is 1, and twice the error of the Gibbs is a bit larger than, okay, it's larger than 1, so larger or equal, then you have this inequality. So, and this inequality obviously holds in the case where the majority vote makes no error, because the Gibbs will in general make some error on it. So in general, you have this, so if you perform, so I have demonstrated this equation for a particular example, just take the expectation on both sides and you have this inequality. So, because it's with respect to the same distribution. So basically, we have this factor of 2 rule, and this is how PAC-Bayes works most of the time. We will provide the risk bound for the Gibbs classifier, and via this factor of 2 rule, this will give a bound on the majority vote classifier. So, okay, so in PAC-Bayes theory, or in the PAC-Bayes setting, I would say, well, the task of the learner is to produce a posterior distribution. So we call it a posterior distribution because the bound will also depend on another distribution, which is must be defined before observing the data. So it's a prior distribution on your set of classifier P. And basically, the PAC-Bayes risk bound, as you will see, will depend on the Kullback-Leibler divergence between the posterior and the prior. So this is just the standard definition of the Kullback-Leibler divergence. Notice that in order to be finite, basically, the support of the prior must include the support of the posterior. Okay, you cannot, otherwise it would diverge if P is equal to 0. So this means the support of Q must be included, must be contained within the support of P of the prior. We will, some PAC-Bayes bound also make use or express in terms of the Kullback-Leibler divergence, but between two Bernoulli distribution, one with probability of success Q and probability of success P. So we will also make use of this quantity, of this function. So this is our main theorem that we have obtained a couple of years ago. We have presented that at ICML 2009. It's quite nice because it's quite general. You can obtain all known PAC-Bayes bounds for classification out of this one. And it's very, very simple to prove. So it is stated as follows. So for any data generating distribution, for any set of classifiers, any prior P, of support H, and for any, so you see here you have this distance between two quantity, a real number, which is a Gibbs risk and Gibbs empirical risk, and the bound is valid for any distance measure or any function, any real valued function. It can even be negative, there's no problem. So for any D, basically this bounds all with probability at least 1 minus delta simultaneously for all posteriors. This distance between the true risk and the empirical risk is bounded by that. So I have already mentioned what is the Kullback-Leibler divergence. Now you see the bound depends on some double Laplace transform, so double expectation with respect to the prior and with respect to the training set. So
less than or equal to, right? Less than or equal to 1 minus delta.
Pardon me?
No, greater than or equal to 1 minus delta?
It's less or equal to that.
I see, with probability more than 1.
With probability 1 to more than, not more than 1, but 1 minus delta.
I see, because it is like, okay.
So, of course, to obtain a bound, this means that you need to upper bound this double Laplace transform. Okay, so, so this is some sort of thing that we can do easily for many cases. Once you are given a D, you can find an upper bound for that, and you get automatically this theorem. So the way to prove this theorem, I'm going to go through the steps so that at least you can, when I'm saying that it's easy, you will say, yes, it's really easy. And this is the art of PAC-Bayes theory. Basically, the idea is to consider this random variable. This is a random variable of S, okay? And we're going to, it's a non-negative random variable because it's exponential of something. So it's a non-negative random variable, and you can use Markov inequality for that. So it's a random variable that is function of S. So the probability that this random variable exceeds t times its expectation is at most 1 over t. So I just replace t with 1 over delta, and there you have it. So this is the basic, let's say, bound that is used by PAC-Bayes. It's Markov inequality. So you would say, oh, this is very bad. In fact, nobody has came out with a better bound with this random variable. I've tried to go to Chebyshev. It does not buy me anything. So I get the same, basically the same bound. So, we're using Markov, and this means that with probability 1 minus delta, I get the negation of that. So with probability 1 minus delta, I have the negation of that, which is this, greater or equal to this. And I take the log on both sides. I took the log on both sides, so it's holds with probability 1 minus delta. And so then the next step, remember the bound holds uniformly for all posterior. So it will be to convert this expectation over the prior into an expectation over the posterior. So the standard trick would be, so f of h is just this function, okay? It's just this function here. So the first thing is, okay, let's convert this expectation over p into an expectation over q. And you would say, well, this is easy. I mean, the expectation over p is equal to the expectation over q, but in fact, it's greater or equal. So basically, you see, well, it's q. So in order to get p, this is the expectation over p. I just introduce q and I divide. They cancel, but we have to be careful when it becomes 0. So basically, this holds for the support of q plus the rest of the support of q, which is in p, basically. So this term is greater or equal than this term. So basically, the expectation of p can be changed into an expectation over q with this. And this is exactly what we need here. We just basically, so you will have greater or equal than the expectation over q. So it's on the right side. It's, okay, so the next thing is to, so we have a log of expectation that we're going to convert into the expectation of a log via Jensen's inequality. So this is the first step. Expectation over p is greater or equal than the expectation over q of this. And then the log of the expectation is greater than the expectation of the logs because of the concavity of the logs. So we have one Jensen inequality here. And so the log of a product is the sum of the log, and basically here you have minus the KL divergence here because it's P over Q and the KL is Q over P, minus the KL plus the log of this. So I remind you that f of h is this is the complicated expression here. This is the exponential. So we apply this, basically this result to the exponential of md. And we just, this is just the application of the formula. And so we're almost done, basically, because the log of the exponential is just the argument. So you see that we find an upper bound. We find that the expectation of md is lower or equal than KL plus this, which is identified in the theorem. But we're stuck with the expectation of md. But the expectation of md, basically, by using Jensen inequality, the expectation of basically of d is greater. We assume that d is convex, so the expectation of d is greater than d of the expectations. So this is it. Basically, you basically then have the theorem that says. So it's not a long proof. You see, every step is there, and you have this bound. But now you need to bound this Laplace transform in order to get a bound. So that's PAC-Bayes theory. Markov inequality and 2 Jensen. That's it. And the amazing thing is that it's simple, but you can have it can be very, very tight. So, okay, so if for D, you're using the Bernoulli, the KL divergence between two Bernoulli distribution. If you're using that for this distance, you can perform this expectation here. So you need to swap the expectation. So this is why P must be independent of S. So you swap the expectation. This is why we need. Otherwise, it's difficult to perform the expectation over P before the expectation over S. So we're going to swap the expectation and then condition this expectation in terms of the number of errors. We know that the distribution of error is a binomial distribution. I'm skipping the detail. We find that. And this is in theta, a big theta of square root of m. So basically, you have a bound. You obtain the same bound that has been found by Langford and Seeger, but a bit tighter because of this square root of m dependence here. So this is one of the famous PAC-Bayes bound that has been found by Langford and Seeger. And this is a graphic illustration of it. So at the first time, it's a bit confusing the way the bound is stated, but let's say to see how it works, basically assume that this fix the posterior. You are interested in some posterior and you want to find the guarantee for this, the upper bound for this posterior. So you fix a posterior. This will be a number because the prior is fixed. So this will be a number, let's say 10% or 5%. And basically, let's plot this function in terms of the real risk when you have computed some empirical risk value. So this is a plot of the function in terms of the real risk when you assume that the empirical risk that you have measured is 10%. And so basically, the KL, this function must be, in terms of RQ, must be lower or equal than this value. So this, you see immediately, it gives you an upper bound and a lower bound. So, and you know that the real risk is with confidence 1 minus delta is between these interval, inside this interval. So if you change the function and you say, well, remember the first argument is the empirical risk. So if you're looking for a function which is linear in the empirical risk, which is a natural thing to do because you have the expectation of something that is a sum of linear, so it's going to be expressible in terms of a product, you find this result basically for the Laplace transform, and so you can choose f to be, you see this is e to the f power to the m, and this is also power to the m. So you say, well, I have a number power to the m, so let's choose this number to be 1. So I will have 1 power to the m, which is 1. So if you choose m to be 1 over this guy, so it cancels out, you will basically have for the Laplace transform log of 1 over delta, which gives you a small bound. And if you're basically doing a bit of algebra afterwards to express r and f minus 1 of the result, well, you get this bound, which, so 1 minus exponential, it's a function like that. So this is x, this is 1 minus exponential of minus x. So this is this function here. So so 1 minus exponential minus x is smaller than the argument of the exponential. So for simplicity, suppose that this term is just c times rs plus 1 over m this. So this is another bound that you can obtain immediately from the general theorem, and its fact it has been found by another method by Catoni in 2007. So it's kind of a simple, it says basically it's valid for any number c, any constant c, any positive real number c, but it's not valid uniformly for all c, but you can, by a union bound argument, make it valid for k values. You will just need to introduce a ln of k here. So, okay, this bound says something simple. If you want to find the predictor, well, the Gibbs predictor with the smallest possible bound, it will be the one which minimizes this plus this. So you will end up by saying, well, what you need to optimize, what you need to minimize is this quantity. So then it says, well, the posterior Q that you're looking should minimize that, which it's a bit like what we have postulated at the beginning. It's some measure, but it's not the risk of individual classifier. You have to measure the risk of the average risk or the risk of the Gibbs classifier, and you have this KL which acts as a regularizer, so which grows depending on how far you are from the prior. So you have an hyperparameter to tune. You don't exactly know its value. You could try to. So you have one extra hyperparameter to tune, which is not the case from the previous bound, from the Langford Seeger case. You have no hyperparameter to choose. So the corollary to 2.1, which is the Langford Seeger bound, gives a bound which is, in fact, so we have two bounds. How do they compare? With the one with the small KL, the one with the KL between the two Bernoulli distribution, gives you a bound which is always tighter except for a narrow range of values of C, which is normally around 1. So normally the Langford Seeger bound is tighter than the Catoni bound. But the fact that the Catoni bound can be tighter is just because instead of having ln of square root of m divided by delta, it has ln of 1 over delta. It's just because of that it can be tighter. If you would have ln of square root of m over delta, then the Langford Seeger bound would always be tighter than the Catoni bound. Okay, so let us apply these bounds, and let us try to minimize these bounds for a certain class of posterior distribution. So searching in the space of all posterior distribution is something very hard. You know, there's too many of them. So let us restrict ourselves to a class of posterior distribution, which will be Gaussian distribution over a linear classifier. So, okay, so each example is mapped. So it will be a learning algorithm which can use a kernel. So basically each x will be mapped either explicitly or implicitly in a feature space phi. And the feature space can often be given in terms of a Mercer kernel. And so the output of the linear classifier is going to be described by this. This is the usual formula when you have a feature space phi of x. So it's the sign of the scalar product with phi of x. Okay, so we're going to be looking for Gibbs distribution which are isotropic Gaussian centered on W. So you have a Gaussian which is isotropic, so you have the covariance metric is unity basically, and it has unit variance. So it's a very simple thing. So it's just an isotropic Gaussian centered on some W. So W is the parameters of my distribution. So I will write Q sub W of V. So this is the density on V parameterized by some W. Okay. So one nice thing about this Gaussian distribution, so basically you have this W, this vector W, and you have a Gaussian distribution, and this board here is the space of all linear separator. So whenever you have an example to classify, so XY here, this is an example, so it in the space of a separator is just an hyperplane. So some of the predictor here, let's say predict +1, some of them predict -1. So basically you see that if you're, and consider the majority vote. So if you're taking the majority vote with respect to this Gaussian, well, the majority vote will be, the weight will be larger on the predictors predicting -1. And this is the output of the majority vote. And you see it's exactly the same as the output of W. And by symmetry, basically, the majority vote and this single linear classifier are producing exactly the same output. So they are the same classifier, basically. So the output of the majority vote is the same as the one that of the deterministic classifier, which is the center of the Gaussian. So basically, this means that twice the risk on the Gibbs classifier. So let's say a bound on the risk classifier will give you a bound on the single predictor W. Okay, this is how it works. Okay, so we define the class of posterior. We need to compute the KL divergence because the bound will depend on the KL divergence between the posterior and the prior. So we will choose a prior centered on some other W, WP. So this is the prior. Most often, WP will be the origin. Okay. If you have not seen your data, there's no preferred direction. So normally, WP will just be the origin. So the KL, because these are two Gaussian, the KL divergence basically can be computed exactly, and this is what it gives. And it's just basically, it only depends on this norm, the norm of this difference vector. It only depends on that. And it's a nice quantity because then you have a regularizer which does not depend on the dimension of the space. And this would be bad that it would depend on the space of the dimension here because this is feature space phi, which can be a very large dimensionality. But all basically, because these are isotropic Gaussian, the integrals, the KL divergence in all the other direction, they cancel. So there's only one surviving direction, basically, that gives you the KL. Okay. So we need to compute what will be the risk of the Gibbs classifier. In order to have a bound at the end, well, you need to say what is Gibbs risk on the training set. What will be Gibbs risk on the training set? So the Gibbs risk on the training set is just the average of Gibbs risk on the individual classifier, on the individual example, sorry. So you need a formula. You need to be able to compute Gibbs risk on any single example. So basically, you need to be able to perform this integral. If you're not capable of finding a closed form and expression for that, you end up needing to perform Monte Carlo simulation, and this would mean a very slow learning algorithm. Each time you need to compute the empirical risk, and this will occur often in a learning algorithm, well, you will need to do at each point a Monte Carlo simulation, so this is not very interesting. So fortunately, Gaussian, you can integrate this, basically. It's just this part. Suppose that it makes an error here, so it's just this volume. So basically, again, all direction cancel, and it's just basically depends on this quantity here. So this is what you obtain for Gibbs risk on a single example. Is just a cumulative Gaussian, basically, which depends. This gamma is the normalized margin between weight vector W and example Y phi of x. It's a number between -1 and +1, and you multiply by the Euclidean norm of this weight vector. So this is Gibbs risk. You can make some plots. So in terms of the margin, so recall that the margin is just it's a real number that gives you it's the cosine of the angle between W and phi, and it behaves like that. So it has a sigmoidal shape. It's called the Probit loss, in fact. So this is a Probit loss. So basically, it gives you a loss function on the example, which has this form in terms of the margin, of the normalized margin. And as the norm of the weight vector becomes very large, then it converges to the 0-1 loss of the majority vote, basically. So it makes sense then to measure the performance of the Gibbs classifier in order to obtain a performance indicator for the majority vote. So if you have large weight vector, well, the performance, the guarantee that you have for the Gibbs classifier with a large weight vector will somehow be a good indicator of the performance of the majority vote. So the way to understand why you have this result, basically, you just say, well, suppose that this, suppose this is your weight vector W, okay, and you have some example here. This is your example Y, phi of x. So if the scalar product between these two are positive, so suppose that it's here. So if the scalar product between these two vectors is positive, then you have correct classification, but it's a Gibbs classifier, okay? It's a Gibbs classifier, so this means that with some probability you can draw a predictor here which misclassify that example, so this is why you don't have a perfect classification. So this is why that as the norm of this predictor increases, it becomes more and more deterministic. Okay. So we have bounds. We have the bounds are expressed in terms of the empirical risk and the KL divergence. We found the analytical expression for that. Basically, what is left then, we should say, well, let us find the predictor W, which will minimize this bound. So this is the Langford and Seeger bound. So we're looking for the W which will minimize this, and the bound is just the largest value of epsilon for which this inequality holds, and this is realized at the equality, but you have two solutions. Remember the plot I gave you? You have one which gives you an upper bound and the other which gives you a lower bound, so you must choose the upper bound. So basically, we're going to try to find W minimizing the bound such that the bound is given by the formula, and you take the solution where B is larger than the empirical risk. Okay, so that's what we're going to do. So it's a pity because you cannot express explicitly B in terms of the empirical risk in the KL. You have just an implicit definition, but you can have an explicit formula if you're for the gradient. So the gradient can be explicit. Okay, so the other bound, the Catuni bound, basically is just to minimize this. And if I express the empirical risk in terms of what we found, we find this expression. So we need to find W which will minimize this. And in the absence of any information about the data, we choose WP equal to the origin vector. So basically, you have you need to minimize L2 regularized Probit loss. This is what you need to do. So you should compare that to what the SVM does. It minimizes a convex inch loss with the same regularizer. So the regularizer used by SVM somehow comes up naturally here. But instead of having to minimize the convex inch loss, you need to minimize a non-convex Probit loss.
So I have a question.
Sure.
So the reason you're getting L2 here is because you chose a Gaussian model for the
Yeah.
So if the theory can say how you're actually going to choose that model dependent on the data, that would actually tell me how I would choose the regularizer.
Yeah. You can use this is where prior knowledge can enter. You could say I will use a Laplace prior instead of a Gaussian prior, and you will then have an L1, probably an L1 norm that would pop up out of that.
Well, it's not even just that it's a Gaussian; it's two spherical Gaussians, and it came from the KL divergence, right?
Yeah.
So it's a very special thing.
Yeah, but if you're using Gaussian for posterior, then it's natural to use it also for the prior also. If you would use a Laplace prior, then you would use some other things probably for the posterior. Something that has a nice KL expression.
But isn't it kind of one of the motivation was that when you present the kind of traditional machine learning framework and you say, I pick the regularization to be this number, and you say, why do you use L2, why not L1, why not L17?
This arbitrariness is present here with the choice of the prior.
Exactly. So you can go back and forth between these and just turn the regularization term into a prior, right?
Yeah.
But Bayesians did that anyway. They always say that the regularization is just the log of a prior.
Yeah, exactly.
So you're doing map estimation. So it's not like it's anything new.
Yeah.
So. Anyway, this is what we find, but we find that in fact, you see this hinge loss this is what we should minimize, and the hinge loss is not quite that. It's a convex relaxation, but it's not an upper bound. Because it can go to 0, it can be larger and then lower on some part of the Probit loss. Okay, so we've performed gradient descent on these bounds, basically. So for the Langford Seeger bound, you can compute the gradient. So I'm skipping the details. It's not very interesting. You can compute the detail for the gradient for the Catoni bound. Basically, you derive this differential of this and things. And then if you compute the gradient in terms of W, well, you have this that pops out immediately. So you will see that I will sometime choose to center the prior on some other W. You will see why in a few minutes. Okay, so why do we use gradient descent? Well, we have a problem here because the Probit loss is... the Probit loss a priori is not a problem because it's quasi-convex. This means that the level sets are all convex. The problem is that we have a sum of quasi-convex function because you sum over all your example, and for each example you have a Probit loss. And the sum of quasi-convex function that is not guaranteed to be convex anymore. And in fact, the empirical risk is not quasi-convex, and the bound, because of that, does have several local minima. Okay, we have seen that on the data. It has several local minima. And you can be stuck on some of them. And this is especially true if you take the Catoni bound with this hyperparameter C. And when C is large, the problem gets more important. So basically, nevertheless, we say, well, the theory says that we should minimize something which is not convex. So let's try to do it. And we tried to do it, let's say, just by doing a lot of random restarts, doing gradient descent with random restarts. And we increased the number of random restarts for large value of C because we had more local minima. And this is what we did, basically. Sorry, I'm stuck. Okay. So each algorithm, well, with these functional expression, you have an empirical loss and an L2 regularizer. Then the representer theorems applies, and you can write W. The representer theorem for these function to minimize will say that W must lie in the linear span of the examples. So basically, we can either work with the primal variable or the dual variable, the alpha, whenever we have a kernel. So we tried both versions. The primal version we compared with AdaBoost, basically, and we used decision sum. AdaBoost seems to perform generally okay, with decision sum. So we compare it with AdaBoost. And the dual version, we use the RBF kernel and compare it with the soft margin SVM, which is the golden standard. Okay, so we propose 3 learning algorithms. PBGD1, so this is for PAC-Bayes gradient descent 1. So we use a non-informative prior centered at the origin. And we minimize the Langford Seeger bound with some confidence delta equal to 0.05. It's not very sensitive with the choice of delta. So remember that the Langford Seeger bound has no hyperparameter in it. So basically, you don't need to try to trade off what will be the empirical risk with respect to the regularizer. It's given in the bound. So we tried that. The other thing we tried, this is version 3 of PAC-Bayes gradient descent, is to say, well, I do not have confidence in perhaps the regularizer will weight too much. Okay, so basically we decided to minimize the Catunis bound, but for different values of C, not necessarily the one that will give the smallest risk bound, but for several values. And we choose the value by cross-validation. So this is sort of okay. So let us try to see if this can improve on the other. PAC-Bayes gradient descent 2 is quite different. In fact, this is a true bound minimizing algorithm. Basically, at the end, you have a predictor, and you really have a guarantee that is valid for that predictor. Here, you're cheating a bit. Here. Okay, you will have a predictor. You can compute the bound. The bound is valid for that predictor, but you're not necessarily using the predictor with the smallest risk bound. You rely more on cross-validation to select your best predictor. Okay? But here, basically, it's another way of getting a risk-bound minimizing algorithm. Basically, here you say, well, I'm going to use half of my data to learn a good prior. So the only reason for the only use that you're going to make for the first half of the data is to learn a good prior. So the priors are isotropic Gaussian centered on some W. So I'm going to try to find a set of W's which would give me good priors. So basically, we minimize the Catoni bound with different values of C. So ranging, 1, 10, 100. We tried very large values. This will give me several solutions.
But I thought prior really has to be independent of the training data.
Yeah.
But now you're sampling the same distribution.
Yeah.
So you get
it's not a correct way of saying it, but basically you have the first part of your training data, and you're just minimizing this the second bound with a uniform prior, the Catoni bound with a uniform prior. So this will give me some predictors centered on some set of predictors. And now for the second part of the data, I will put the prior centered on those. So they are independent of the second half of the data.
But the second half of the data was the same distribution as the first half. So
Yeah.
So you can't swap the expectations. It's not legal to swap the expectations anymore.
Yes, because it's not the same. It's
conditioned on now. You know what I mean? You've conditioned on it because.
Yeah, but as long as you're computing the empirical risk on data, the prior didn't see the second half of the data, so it's okay.
Right, but he's taking an expectation deep in theory. He's taking an expectation over drawing samples from D, and he's swapping it with the.
The prior can depend on D. It just can't depend on S.
Yeah.
Prior can
Depend on D.
depend on D in any way you want.
Okay.
So yeah, so this is basically, so for the second half of the data, basically we do the same thing as PBGD1. So basically we minimize the Langford Seeger bound with no hyperparameters for priors centered on these solutions that we found for the first half of the data. And basically we keep the solution having the best bound. So this is really a true bound minimizing learning algorithm, but where we can cheat on the first half of the data to find better prior than just the uniform, the non-informative prior. But we lose. We will compute the empirical risk. We lose by this process because the empirical risk is going to be computed only on the half of the training data. So.
Reason for choosing half as opposed to quarter or any other number?
We tried all the fraction, and I don't know why, but half is the better. Half gave the best result.
So Mario, you're doing two things here, right? So one is you're trying different C's, and the other is you're splitting the data into two halves. So if I were just to use the two half trick. So namely, I use maybe the Langford Seeger KL bound, and I just learn one W on half the data, and then I take the second half of the data and I learn another W, which is regular to be close to the first one.
It does not buy you anything, because it's basically you will obtain the same solution as you would have trained on all the data with the non-informative prior.
But my bound in the second randomization is now nothing, because I'm assuming that if I train on half the data and then I try to get on another random half the data, it's not going to change the solution by much. It's just the variance of the data somehow.
The bound will be smaller. I guess.
You're realizing something which is going to be almost exactly. So I'm saying you're doing two things here. The second thing, the optimizing of C, maybe is not needed.
Well, this is a way where basically you can obtain very large weight vectors. Whenever, it's not clear what it will give you. I don't recall exactly what it gave. It buys us nothing at the end. But to say that you will obtain a better bound, the empirical risk might be quite large. Still, it might be the case that you find weight vector that have small norm, and because of this Probit loss, you will have quite a large empirical risk, 10, 15%, and this will contribute to the bound. Here, basically, by having large weight vector, basically the empirical risk that you're going to find on the second round is going to be smaller. So basically, the weight vector is going to be close to one of these very large. It's just going to slightly adjust around it, and so you will have small empirical risk and small KL divergence. So basically, the ones that were preferred by this trick were the ones with large weight vectors, generally. So these are PBGD1 and 2 are true bound minimizing learning algorithm, but not this one, basically. You rely on cross-validation for the hyperparameters. So you're minimizing a functional which is inspired from the bound. The quantities are there. You're using the Probit loss. You're using L2 regularizer, but for the respective weight, you're relying on cross-validation for it. This is PBGD3. So let's compare these results. So we don't have a lot of data as in Microsoft Research. So we rely on what is publicly available. So UCI, MNIST, and so on. So basically, the results are we have split the data depending on the data set, but normally it's usually half and half. Basically, we train on the first half, and then the testing score, we compute the empirical risk on the remaining half of the data. And we perform the binomial tail inversion test of Langford to determine if difference in empirical risk is statistically significant or not.
That's not a match test. That's kind of a bulk test.
Yeah.
It's not like McNamara's test. It's just some sort of.
Yeah.
I don't know the papers. It's just some sort of statistical level.
Yeah.
Okay.
So basically, you need to compute a test bound, a test upper bound, and a test lower bound, and if they are disjoint, basically the difference is statistically significant. Otherwise, it is not. So these are the results in the Primal case for decision stump, and basically this is I'm sorry, the bold ones are the ones that have better results, but they don't show up quite clearly, unfortunately. So I should have put some colors in it. So basically, this is the result for AdaBoost, the risk computed on the testing set, and the bound. You can compute the risk bound that we have for AdaBoost. This is PBGD1. PBGD2, if you can see for the bound, we obtain better bounds. For instance, on mushroom here, it's 3% for the bound with respect to PBGD1, which gives you 13% for the bound. So by this trick of using half of the data, we can obtain really lower bounds, better bounds. And PBGD3, well, this is the bounds, the guarantees are worst, But the actual result seems better. Overall, I would say that this is a winner. So the statistical significant difference is here. There are almost always no statistical difference except on these cases. For instance, AdaBoost is statistically worse than a PBGD 1 and 2 and vice versa. So, or perhaps it's better, yeah, better. So better, yeah, so, and here 3 is better than 1, and so on. 2 and 3 are better. The worst one actually is PBGD 1, just doing the straight risk-bound minimization with a uniform prior gives you generally much worse results than PBGD 2. And PBGD 3 is still an improvement if you rely on cross-validation for the respective. So it gives you better results, which are quite competitive, let's say, with AdaBoost.
So Mario, do you have a sense of how much of this might be optimization problem? The reason why I'm thinking is that Lou Mason, in sort of the context of AnyBoost, suggested using something very similar to the Doom 2 loss, which is a tangent on a Probit, but it's almost the same. And so he was getting, I think, better results than AnyBoost. I don't know if it's exactly identical, but I just didn't know it could be an optimization thing. It might be not the loss function itself. I mean, did you try? You tried multiple restarts, right?
Yeah, that's what we tried. It's not indicated what in their paper what they have tried, although. Well, it's just boosted, yeah. So.
Just a different, you can think of it as different optimization techniques.
Yeah, but you will end up in some local minima for sure.
That's true.
Yeah, and there's no regularizer, but you stop boosting after, let's say, 200 rounds.
So kind of the main motivation was to say we'll get a relatively tight bound and try to optimize with respect to that. So this evidence doesn't exactly support.
Yeah. It's better. It's still better, basically, to tune the weight between the regularizer and the empirical risk by cross-validation. Generally, it's better. So this means that the theory somehow has to progress a bit. Yeah. But still, PBGD3 is a learning algorithm that inspired from the bound because we're using the loss that was given by the Gibbs risk. And we're using the regularizer that came out with the Gaussian, which is just an L2 standard thing, but it's, let's say, a bound-inspired learning algorithm. But quantitatively, you need to basically tweak the balance. Yeah, that's that. So this is the result we have with the RBF kernel. We compared with the SVM, and the same sort of picture. This is the worst algorithm, worst result. These are better. And this is still better. And what is nice is that the bound can be quite low here, basically 1%. This is a true risk bound is 1%, and it's basically it's doing better than that. It's 1%, but still it's nice. It's nice to see that on adult you see the bound is sort of quite close to the actual risk. Yes.
Sort of to get to John's point again about the optimization, I don't know if this question even makes sense, but can you take the weights learned by the SVM and apply it to see what bound you would come up with? If you
yeah. Well, we can take the solution of the SVM and compute the bound, the same bound that we.
So that's what that bound is.
Yeah. So they are worse. So.
Okay.
The bounds say, well, you should not pick this solution. You should pick, in fact, this one, which is better, but this one is even better. It has a higher bound, but.
Okay, so the optimization is finding a lower bound than the SVM. It's just okay.
Yeah. For sure, the bounds here are worse than this one.
I see.
Okay, so.
Going back to that, so it seems as if there is still a slackness in our bounds. Do you have any feeling to what is the source of the slackness?
Well, the regularizer seems somehow too strong. But so it's difficult to get rid of it. And in this setting, I could not get better bounds than that. This is really.
And indeed, when you look at the choices of the kind of the in PBGD3,
Yeah.
you see that it gives smaller weight to the.
Oh yeah. Definitely, these are the best results. You multiply the empirical risk by 1,000. So this is pretty good. So this means that the weight on the regularizer is just too strong. Yeah. But PBGD2 is sort of, you say, okay, I know that, so I'm going to cheat on my first half of the data in finding large weight solutions, and then on the second half, the regularizer is smaller then. Oh,
Sure. Digging into the same. So maybe I'm interpreting the bound wrong, but I thought what the bound really says is if you were to keep sampling test data, you will be above the bound only 5% of the time.
yeah.
It doesn't tell you anything about what your average risk is going to be if you average over those. So I don't think it's really that surprising that you're on an app. You drew your test set, you ran the classifier, and you got something that's way below the bound, because the bound is talking about your tail loss, right?
Yeah, but this is you need to bound the tail. You need to bound the worst case.
Yeah,
I mean,
the results you show are not worst. You're evaluating the average case and the results that you showed, but the bound is giving you a guarantee on worst case. So I don't think that there may not be a slackness between the theory and the practice, right? Because you have to run this many times to see.
So would you say that maybe some of these algorithms that seem to be performing better actually have larger variance, and we don't see that?
And we don't see that because you only get one test set.
But another way to say that, or another way to look at that, say that the examples that you tested it on were too easy, and that you could perhaps create some synthetic data sets that would be much harder for the standard algorithms, but your bounded algorithms would do reasonably well and would know how well they did. The distribution of examples should be harder.
I don't know.
Your proofs are for any distribution of samples, right? But the letters A compared to B, that's not a particularly tough distribution of samples, I would assume. Whereas maybe you could make one that would be much harder.
But this has.
It holds for all D and for all Q. It
Yeah.
holds for every posterior and very distribution of data, specifically the worst ones. You're saying maybe the ones that I have are not the worst ones.
Yeah, I don't think those are that bad. So this is getting back to the thing that maybe there really isn't slack there,
Yeah, but-
if you assume it can be any D.
No, but then the question is, okay, how much do I lose by the fact that I'm worst case? And the answer is, one Markov and two Jensen.
From Gibbs to.
From Gibbs to Bayes to the majority vote. Yeah.
It's two Markov and four.
Okay, so conclusion, basically, PBGD2, the second one is better than the first one. So using half of data to learn a prior really helps, basically. PBGD3 is better than the other one. I should not say better. I would say more definitely better. It's a bit better, but I think it has a true advantage. So the bound is a bit worse than cross-validation for finding the proper trade-off. So PBGD3, which is inspired from the bound, you take the quantity that came out from the bound, seems to be very competitive with AdaBoost and SVM, but they are much slower because you have several local minima. So what we have done afterwards is to convexify. So we have this Probit loss, and basically we say, okay, we have all these local minima problems, so let's just convexify it by a logistic loss. So you take the slope here and you go linear here. So this is sort of different from, let's say, the hinge loss, but
It's just logistic regression.
very similar to L2 regularized logistic regression. And So if you do that, you find almost identical result, very, very, very similar. I don't show the number, but it's almost the same thing. But with basically, so this is a bit disappointing. I was expecting to obtain much better result because of non-convexity, saying, well, this is what you have to do. Okay, you have to work harder, but at the end you will find better solution. And no, basically you can just use the logistic instead of the Probit loss, and
I think Carl's right, because usually the excuse for having these non-convex loss functions that go to zero derivative for very wrong things is if you have active like label noise in your data. In fact, it's like an adversary coming and trying to smash you, and that's why you're trying to minimize this sort of. So if your data has no adversary, like, I think you should go through MNIST and like put in like 10%.
We have tried putting classification noise, and there was no improvement between that. But somebody at ICML or NIPS from Google gave a talk, and he did similar experiment, and he sort of imbalanced the noise between the positive and the negative, and then he saw a difference. But we didn't do it. We didn't thought about it. It was better to use the non-convex one. The non-convex one in that case.
So you said the sum of quasi-convex functions is not necessarily quasi-convex, and here you're approximating one quasi-convex function by a convex function.
Yeah.
So if you can do that for the sum, maybe that would give a better convex function. Although probably I don't know if that would be more complicated to minimize.
So not for each individual one.
Yeah, just
how can you do this?
no. So you can take a convex envelope, for example.
The convex
Envelope, yeah. Maybe if
the
it's
sum of many quasi-convex functions.
Yeah.
I don't know if that would work well, but I'm just wondering.
It must be a lot of hard work to do. I don't know. I never thought about it. So anyway, the second one seems the best choice if you want to obtain a good guarantee. So this is part of the work. Now, the second part of the talk, I would like, how much time do I have left? Very little. Oh, shit. Okay. So the second part of the, how much minute? 10 minutes? Okay, so I'll try to go fast, but this is much more recent work. So basically, okay, we have a set of classifier that we call sample compress. So what is a sample compressed classifier? Well, a sample compressed classifier is described by a subset of the training set that we call a compression set, and a message, which here is going to be a real number between -1 and +1, and a bit, an information bit plus or minus. So these are not actually message, but this is the standard terminology in sample compression. So, and we're going to use an auto, and we'll see why, we're going to use an auto-complemented set of classifiers. So basically, for each classifier, the negation of this one is going to be by definition -1. So, okay, let's give you an example of a set of sample compressed classifier. These are the ones made by a single example. So suppose that, okay, so this is an example of a sample compression set of classifiers described by only one training example. And I'm going to use any bounded similarity function for that. Okay, so I will normalize it to 1 between -1 and +1. So each classifier is going to be described by a single example and a message, sigma ns, such that h plus here, this is the definition. It's going to output +1 if sigma is less than the kernel value at x. Otherwise, it outputs -1. So you can write it, I like to write it compactly like that, the sign of this predicate. So if basically the kernel, the similarity function evaluated at x, so this is the one used for describing this classifier. If this distance is greater than sigma, well, I'm outputting +1, otherwise I'm outputting -1. And so the Boolean complement of this is just going to be minus the one after the plus. Okay. So I can produce, so this is an example of simple compressed classifier made of a single example. You could took pairs of example and define an hyperplane. You could take an whole bunch of example and run an SVM, and this will output a classifier. So basically, it's a simple compressed classifier where the compression set is the set of example that you have used. So we're going to be interested in building a majority vote of such simple compressed classifier, and we want to obtain a PAC-Bayes risk bound for majority vote of simple compressed classifiers. So basically, each sample compression is going to be described by a vector I, which points to the individual example used used for defining this classifier. So we have a prior on this set of sample compressed classifier, which not a prior, any posterior distribution. And this distribution, it will be written like that. So you have a distribution on the subset of the training set that is used to construct your classifier, and some distribution on the message given the compression set. Okay, and we're interested in this guy here, the majority vote of these sample compressed classifiers. And we want a risk bound and design a learning algorithm to minimize the risk bound. So consider again the case where each sample compression set, each compression set is made of a single example. So we're going to use a posterior like that because it's quite natural. So you have a distribution on your index. So each example can make a single classifier. So you have a distribution on I, a distribution on the sign. That is, you have, for each example, you have a pair of classifier, one which is a Boolean complement of the other. And in fact, you have a continuous also. You have continuously many because you can have several values of sigma. So we're going to use the uniform distribution for sigma over -1 + 1. And I'm going to use this weight, which will appear in the expression of the sample compressed classifier, which is the weight assigned to that example and the difference between the plus and the minus. So the weight is bounded by this value, but it can be positive or negative. So these are interesting because a majority vote of sample compressed classifier basically can produce any SVM classifier. So pick any SVM classifier, you can express it as a majority vote of sample compressed classifier of size at most 1. So you can realize this if you just look at the output function for any x of a majority vote of sample compressed classifier made out of a single example. So this is the expectation. So you sum over all possible example used for some sample compressed classifier, sum over all sign, the integral over the uniform distribution of sigma times this. And basically what comes out is this expression at the end. So it's the sign. So basically you can generate any weighted combination like that, but WI is bounded, but it does not matter because take any classifier, you can always divide it by the largest, because of the sign, you can always renormalize the weights. So basically, these majority vote of sample compressed classifier of size 1 are interesting because they contain all the class of SVM. But here we use any similarity measure, so we're not restricted to positive semi-definite kernels. And we have a bound which is valid no matter what is the similarity measure out of it. Okay, so the way to go from the majority vote to Gibbs is usually that, but here it's not good. Here it's not good because in the case where the sample compressed classifier are made of a single example, they are very weak classifier. They are not strong classifier. They will almost always make error. have an error rate which is close to 1/2. So Gibbs error rate will be close to 1/2. So it's not a good measure of the performance of the Bayes classifier, because Gibbs error rate will be close to 1/2 even if the majority vote is 0. So by probing the Gibbs error rate, it does not inform you at all in this case on the performance of the majority vote. So we need some other things than Gibbs risk to monitor the performance of the majority vote. And so to see what we need to use, let us consider what would be the expression of Gibbs risk. So this is the expression of Gibbs risk. Okay, so it's just the expected expectation of the real risk. And basically, you can convert this indicator function in terms of the margin. So y h of x is either +1 or -1. So if it's +1, it's an error of 0. If it's -1, it gives you an error of 1. And so here, I'm going to define the margin of Q on example xy to be this expression. It's usual notation. And basically, the risk of the majority vote is at most twice the Gibbs of risk, which is just then equal 1 minus the margin. But 1 minus the margin is some linear function of the margin, which has nothing to do with the step function of the margin, which is the risk, Bayes risk. So this is Bayes risk for the risk of the majority vote, the 0, 1. This is 1 minus, so it does not, this is 1 minus MQ, the equation for, and so basically it does not make any sense to bound Bayes risk with this function, okay, if basically most of your example are around here. So have small margin. So what we're going to use instead is a loss function like that, which is a quadratic function centered on some margin, and that can be chosen any value, basically. And so if you find distribution for which, all the examples have small margin, then it makes the quadratic risk is a better measure than this linear risk for this case. So basically we're going to use this, and the bound on the expected loss for this quadratic risk also provide a bound on the majority vote. So, and if you would use a linear function which is more inclined to this, it does not work because it's negative, and you have to upper bound the risk of the majority vote. So, so this is the bound we have. So the bound is actually valid more generally than just the quadratic loss. It's valid for any loss function that has a Taylor series expansion around the 0 margin. Of a finite degree, okay? So this is the result that we have, basically, for all posterior distribution, align on P, and I will tell you what align mean. The risks of this loss function, which could be the quadratic loss function, which also bound the risk of the majority vote, it's less than the empirical measure plus there's no regularizer. There's no regularizer, but there is this constraint. Plus this, just this confidence interval is square root of m. Instead of m, you have m minus d. D is the size of the sample compression that you're using. If you're using a single example so d is 1, you might use 2 or 3. This will give a deterioration of the bound, and the degree here of the loss, which here will be 2 if you were using the quadratic loss. So it's kind of a nice bound because it applies for any sample compressed classifier, which are defined in terms of similarity function, and you're not restricted to use Mercer kernels or whatever. It could be it can be even non-symmetric. Okay, so there exists a risk bound that applies to non-PSD kernel. But what they have is that they have an empirical risk which must be measured on part of the data. So basically, the way they are constructing the classifier on some part of the data and measuring the empirical risk on the other one, whereas this is computed on all the data. So basically, this is a better bound than what has appeared before. So we have been minimizing, okay, so a few words on what does align mean.
I think we need to wrap up, so
Okay.
if we can quickly...
So align means just that you have pair of auto-complemented classifier. Basically, the posterior weight on a auto-complemented pair is always equal to the prior. So the only thing that the posterior is going to do is shift weights from one to the other. And even with that constraint, you can produce any majority vote. So it's basically not a constraint, but it gives you a good bound. So this is, and it has no Kyle divergence. This is the proof. I'm going just over it. So basically, we have used this bound to derive algorithm, and it gives very good results compared to SVM, for instance. This is the aligned case, the non-aligned case, where you have a KL divergence. So it gives good results. State-of-the-art results, in fact. So we're pretty satisfied with that. So basically, yeah, okay. So I'm going to...
So how is it different from regularized least squared classification? I saw you guys tested versus regularized least squared.
Yeah.
Is it what's the net result? I mean, is it different?
The solutions are different, but here it's an L infinity constraint that we have. The weights are restricted to be in plus minus, and here basically you have an L2 regularizer.
So it's in a box.
Yeah, it's in a box, exactly. Okay, let's me wrap up by saying that we have a PAC-Bayes bound which compares favorably to currently existing bound because it applies to non-symmetric positive definite kernel. Minimizing the risk bound really gives state-of-the-art results. It's pretty good. The work can be extended for multiple kernel learning. That's what we're working on, and perhaps a few words that we're doing sample compress MKL right now. We want to apply that also to random forest because random forest is also sample compressed classifier where you compute the empirical risk on is the out-of-bag estimates basically. So we want to do the approach random forest from the PAC-Bayes point of view. I'm also quite involved in PAC-Bayes structured output prediction, and basically we want to apply that to peptide inhibitor prediction. So you have a protein, we want to predict what will be the peptide that will bind strongly to a given protein. So thanks a lot for your attention, and I'm sorry to have exceeded my time.